So we doing okay with this equilibrium stuff so far? I mean, basically what we got here is if sum of forces is 0, which would be if acceleration is 0, we can find what we call the reactions. So we know that the forces have to be balanced in the x and y directions. Okay? I mean, that's basically the deal. Now, you do want to draw a good free body diagram for this, so we want to be sure that we're being conscientious about that. So you want to figure out what it is you want to draw the free body diagram of, and then you want to draw a boundary around it, and then draw in the forces acting on the body, the object. Body is just another word for object. So contact forces are caused by physical contact, so you want to look for things that the object contacts. And then body forces are caused by gravity, primarily for us. There's other force fields that can cause body forces, but we primarily use gravity in this class. Okay. So there's a few kind of things on these free body diagrams I want to cover, some special types of forces. The first are cables. All right. So cables are just a fancy word for a string or a rope. Now, a couple of things. First thing is a cable can only pull. That's all a cable can do. I can pull up in this weight here. For those of you in class, I've got that weight shown on the, those of you online, I've got that a cable attached to a weight similar to the photo you've got. But what happens if I try and push with a cable? You know, not too much, okay? So just be aware of that. All a cable can do is pull. It's got to be in tension. Can't be in compression because it just doesn't support a compressive load, okay? Now the other important thing is that the cable, the force is directed in the same direction as the cable. So if I just let that weight hang, the cable's vertical, it's exerting a vertical force on the object. If I want to exert a vertical force on the object, I can't have a horizontal cable. It can't exert a vertical force on the object, right? I mean, I would just go like that. I would contrast that with a 2x4 or a notebook or something like that. I could have the notebook horizontal. I've got the weight on a notebook now for those of you online. But I can push up with it, can't I? But see, I can't do that with a cable because it has no rigidity to it. Right? So the practical part of that is that if you know the angle of the cable, you also know the angle of the force that it applies, whatever angle that happens to be. That is not the case for a rigid object like a board or, as I just said, a notebook or a steel beam or whatever, okay? So that's what you want to know about cables. Okay, so that's what we know about cables. Any questions on that bit? Yeah, question?
So if you have the force of tension pulling up on a given system of analysis, would you draw that out on your axes that's pulling up in the same direction?
Yeah, it would be pulling, right? And it kind of depends, which side of the cable you're looking at, which direction it goes. So like if my hand is holding this cable up here that I'm showing, if I'm drawing a free body diagram of the weight, then the force is that way, pulling up. If I'm drawing a free body diagram of my hand holding the string, it would be pulling down, So it just depends, what you're looking at, but it's always pulling is the idea. Is that good? Okay. All right. Other questions? You doing all right? Okay, the next thing then is a pulley. Now what a pulley does is it allows you to change direction of a cable. So you know, if you have a pulley, the advantage of that is you can pull down and still lift something up, right? So that's kind of handy. You can, you know, often it's easier to pull down than it is to push up. So with a pulley, you can do that. You can change the direction of whatever you're doing and you know, change the direction that you're pulling to lift something. So I can pull down to lift this object. I can pull at an angle. I can do whatever I want. I lift the object. Okay. Now we've got. Now what we do here, we assume that our pulleys are frictionless. So that's the assumption we make in this class. We make a lot of assumptions, you know, just to make problems workable. And so if we have a frictionless pulley, what that means is the force is constant throughout the cable. So for instance, if I cut a free body diagram around this thing and I cut it like that, the cable would be pulling in both directions. So my free body diagram inside that circle or whatever I drew there would look like that. I'm going to have two poles on the cables, and they would be equal to one another. As I show up there, 160 newtons. If it's the same cable, the forces in both sides of the cable are equal. Okay. We're good with that? Okay, and then the last thing I've got is a spring. All right, now a spring now if you have a spring that has a constant wrap and a constant diameter, you have a linear spring. If it's made out of the same material throughout, it's got a constant diameter and a constant wrap on it. So basically it's in the shape of a cylinder with a constant slope on the spring as it wraps its way up the cylinder. It's a linear spring. What that means is there's a direct relationship between the amount of stretch in the spring and the force. Okay? So what you have then is a spring constant, K, which is expressed as a force per unit length. So in this example, I've got 60 newtons per meter. So what that means is for every meter of stretch, I get 60 newtons of force. So if I have 0.4 meters of stretch, I'd get 0.4 times 60, 24 newtons of force. Okay? And it's a constant relationship. Okay? So I would contrast that with a nonlinear spring, which might be conical. Conical is a common shape for those. And nonlinear springs, what they have is they don't have a constant relationship between the amount of compression or stretch in the spring and the force. So conical springs look something like that, okay? So there's a good example right there. I mean, you're not gonna, the more you compress that, you know, the force will change depending on how much compression you have in that spring. That's the deal with that, okay? Generally in this class we'll work with linear springs, but there are, you know, different types of springs, you know, that are used, okay? All right, so what you have with those linear springs is just a spring constant that gets you the relationship not between the length of the spring, but the amount of stretch or compression and the force. Okay? All right, so why don't we have a look here at an example of how we would proceed with this equilibrium stuff and deal with these free body diagrams. So we got a ring there, and I don't know what page this is. It's 200 and some, 240 or something. I don't know,
244.
244. Okay, thank you. 244. Got a ring that's held in equilibrium by the two masses in the spring. The mass of ring A is 4 kilograms. The unstretched length of the spring is 0.8 meters. The spring constant K is 450 newtons per meter. The pulleys are frictionless. Find the mass of B and C. Okay. So if you want to find, what we're going to do is we're going to find the force in the cables that holds this thing in equilibrium, and from that we'll work our way to what those masses have to be. So what are you going to draw a free body diagram of to find the forces in the cable?
A,
Okay, yeah, why are you going to do A, the ring?
because that's getting acted on by both the weights that we care about and by a force that we can easily figure out.
Okay, yeah, we got two important things that that A have. Okay, the first thing A has is both cables are attached to A. They cause contact forces on A, so we can go that we want A is a good reason to start. The other thing we've got is we can figure out the things we want to know, which are the forces in the cables. Okay, so we have some sort of force relationship around A that we can work with, and the two unknowns that we want are attached to A. All right, so what I would do then is I would draw a boundary around A. Okay. Okay, so to find the forces in the cables, draw a free body diagram of the ring. So FBD means free body diagram. It's like my spelling's a little weak there on draw, but anyway, you get the idea. Draw a free body diagram of the ring. That way you can relate the two cable forces to each other, the weight of the ring and the spring force. That's why we're choosing the ring. Okay, so I've got the ring put right there. I'll do a little bit of the calcs initially for you. So what we've got here is the mass of the ring is 4 kilograms. Now that's metric, so I'll factor that up by 9.81 meters per second squared and get the weight, 39.2. Then I'll find the stretch in the spring. The spring is 1.42 meters long, but the unstretched length of the spring, if it's just sitting there laying on the table with no load on it, it's 0.8 meters long. So the stretch in the spring is the difference between those two things. It's 0.62 meters. Okay? So when I'm calculating spring forces, I use the amount of stretch or compression, not the length, but how much the spring is stretched or compressed. And then I'll factor that up by the spring constant, the 450 newtons per meter, and I'll get 279 newtons. Okay? So why don't we all, just for fun here, draw up a free body diagram of the ring. Okay, now step number 1 when you do this is to draw a boundary around the ring. So there's the boundary. I do that so that way I'm sure that I pick up any contact forces. If I cut a boundary around the object, I'll find the contact forces. Okay. So there you go. So using that little boundary there in red, why don't you draw a free body diagram of the ring, okay? And just take a couple minutes and do that. And the reason I'm kind of emphasizing this is you've got to have a good free body diagram to get the right answer. If you don't have a good free body diagram, you're not going to get good answers to these kind of problems, okay? So we want to be sure we start with a good free body diagram. Or sometimes I just call them force diagrams. Whatever you want to call them. You doing all right on that? So just get the forces. And this is the first step in this process, okay? It's just to turn it into a picture with forces acting on it. That's where we want to start with this stuff.
diagrams are just different.
Okay, so what do we got going on with this ring? We got two cables on it, right? Which way are they going? Cable AC, is that going up right or down left? Up right, yeah, okay. Because we're showing what it does to the ring. It pulls on the ring. That's what cables do. And we've got that angle. That's 20 degrees, I think. Is that right? Okay, 20. Okay, and then we got the other one that's pulling up left, and that's at 60. Okay, here we go. So we've got that, so I'll call that FAC, and then I'll call that FAB. All right, and then we've got the weight, which I calculated there at 39.2. I'm putting that on top because I got another one to show. I'll put that on the bottom. Where you put them really doesn't matter as long as they point the right way. And, you know, in a simple object like this, it doesn't matter. All right. And then the spring force is 279. Is that up or down? It's down because what I'm doing there, that spring is too long. I've stretched it out. So it's going to respond by resisting that stretch. It's going to pull down on the ring. Okay, so that's 279 newtons. Okay, so there's the free body diagram I've got. Any questions on where that's all coming from? Everybody good with the spring going down? Okay, because it's stretching, so it responds by pulling back. It does. Okay. Okay. So I got that going on there. So that's really an important step, is to get a good force diagram going there, okay? Now the next thing I want to do is I want to start solving for the two unknowns, FB and FC. Now what we have now is two tools we can use, not much, but we got a couple of them. Now remember that when you do forces, you're dealing with vectors, okay? So we treat them like vectors. So sum of F equals 0 is the general equation I've got, but I'll refine that a little bit. See, I can get two equations out of that because this is a two-dimensional problem. So those are the two equations I can work with this stuff, okay? So we're going to have to do a bit of trigonometry here, break stuff into components, and add stuff up in given directions, x and y, set them equal to 0, and then we'll be able to solve for the unknowns. Okay? Any questions on that? Okay. Okay. Now, I do want to think a little bit ahead on what I'm doing here. See, I've got two equations. I'm going to have two unknowns. I'm going to get into a system of equations on this, unless I could get a little tricky and avoid it. But if I just use standard methods, I'm going to get two equations, two unknowns here. I want to start with a simpler equation and substitute into the more complex one is generally the easiest way to do these. Now, of course, on homework, you could just program them into your calculator and hit solve and knock them out. That's fine. But on a test, you won't really have that option because you got to use a simpler calculator. So, so what we're going to do here, we want to kind of think about this. Now, I would start with the simpler equation first with the intent of setting up the substitution. Okay? So we're going to use the equations of force equilibrium twice, sum of Fx equals 0, sum of Fy equals 0, solve the two equations with the two unknowns. Now, I would start with sum of Fx equals 0. It's the simplest equation because it doesn't include the spring force or the weight. So using sum of Fx equals 0 will allow me to set up a nice simple proportional relationship between Fb and Fc that can be substituted into sum of Fy equals 0. So that's why I'm doing this. It gets me a nice simple little relationship I can substitute into the next equation, okay? So that's my reasoning for doing this. So what I'm going to do, I'm just going to write up sum of Fx equals 0, and then I'll walk on through it and relate Fb to Fc is what I'm going to do, okay? So that's how I'll approach that thing. So sum of Fx is 0. I always write that down. And what I got a 60-degree angle for Fb, and that's to the left. So that's a negative cosine 60 Fb. And then plus cosine of 20 for Fc. Plus because it's to the right. And I know that that's in equilibrium, so the sum of those two forces, those are the only forces in the x direction, the sum of those two is 0. And what I can do then is I can go ahead and set that up. And I dropped a negative, didn't I? Right there, that should be negative. So when I bring that to the side of the equation, it's positive then. So I get 0.5 Fb is 0.94 Fc. So Fb is 1.88 Fc. See, so that's why I use that sum of Fx equation first, because it gets me a nice simple relationship to work with, okay? Any questions on that? What I'm doing there and why and all that? Okay, so you too can do statics equations. So why don't you go sum of Fy and set that equal to 0. Now you are going to have to pick up the weight and the spring force when you do that, okay? So just go sum of Fy equals 0 and see what you can do with that. I just use that sum of Fx as a model for how you do it. I mean, you're just going in the y direction. So. That question's just that. Probably have a very smart person sitting next to you. You could ask them. Not quite that bright, but you could ask me to make one. especially in mechanical types, you're gonna be using MATLAB a lot. You're gonna get into multiple equations and unknowns that are a little bit messy. You're gonna have to plug into them and get answers out. You know, these multiple equations and unknowns do get a little messy sometimes. So yeah, I learned first how to use the solver on your calculator. I mean, it's a handy thing.
I broke down the forces of every diagram, so I assigned it to my force. And so the cosine components of the two, because the things are equal, and the sum of the sine of the equals the sum of the weight of A plus the spring.
So what I've done this physics style. I took the x equation here. With AC equals 16. Okay, then I have the formula for FAB. Put that into here, which is my Y formula.
You need to use
Okay, so this is the amount of spring force per F we got here. Put that in, I get that AC, and roll that out. Put it in here.
So you got, this is your natural length, but it's
So
distorted.
there's multiple ways or things you can go about this, so now I'm just trying to figure out what
You know, that how much force the spring is to try to get back into its natural position.
Why I solved for the.
Y'all getting that Y equation okay?
Yeah, so there's your.
Then I just do a substitution after I did it. Y'all doing okay with that? Any questions on that? What's going on with that? Okay, so we good with that? Pretty straight up, just a bit of trigonometry here. But just follow these methods, we'll get into more complicated problems. We want good habits developed, so, as these things get trickier, you don't want to be taking shortcuts. You just want to just do this, sum of f(x) equals 0 equals, write it down, and then solve it, Get that free body diagram first, okay? Yeah.
On your exams, are you gonna have longer problems in like few of them or small problems?
I don't know. I'm trying to, I like shorter ones because I can grade them easier. but usually in engineering it's pretty inevitable to have a few longer ones too. They're not like the short little, so the question is what kind of problems do I have in exams? They're always long. I get the impression like on physics you get like a whole bunch of little ones, like bang, 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 and I don't do that. I mean, I might, on an exam, an hour-long exam, I might have as few problems as 3, but usually I have more, and as many as 8, somewhere between. That's the range. I mean, that's about the best answer I can give you. So they're not real like short, real short. Yeah, they'll be kind of similar to homework problems. Some might be a little bit more focused on a particular thing because I know you got that time constraint on the test. And I'll get you some sample problems of old exams because I know that matters a little bit going into an exam, what it might look like. So I'll get you some sample problems. Okay. All right. And they're in Moodle now if you want to look at them. They're okay. Okay, so we good? We got any questions on some of FY? Are we doing okay? Questions? Okay, we good? All right, then we have a fair number of calculations to do on this. You know, and this is why, you know, it's good to know how to use whatever tools you've got. I mean, my order of tools that I use, I've got an HP calculator I can program if I need it, and then I use Excel. Again, you mechanical engineers, they'll push you towards MATLAB next year is what they'll do. So the more comfortable you can get with that this year, the better, I think. So what I've got then is I've got that FB is 1.88 FC, and then I've got that sum of FY equation there. So what I'm doing there, I'm just working through the substitution on the two equations and the two unknowns. So there's my FB equals 1.8 FC, which 1.88 FC from the sum of FX equation. And then I go ahead and I've got my Y equation here, and then I just substitute the 1.88 FC into it. So that gets me one equation with one unknown that I can solve. I get FC as 162 newtons, and then I can go ahead and solve for FB. So that's the forces in the cables. All right, so now I'm not done yet, because what I wanted to know were the masses, right? Okay, the masses that are hanging off those cables are what caused the force. So I need to back into the masses also once I've got the forces in the cables. It's easy enough to do because weight equals mass times gravity, so mass is weight divided by gravity. I mean, that's all I got to do, but that is a necessary final step on this thing. Okay. So I just take the forces divided by gravity and I get the masses.
Why isn't the 318 negative when it's on the top?
That's a good question. Why isn't the 318 negative?
Everything equals 0, right? And then don't you bring the 318 over the other side?
Yeah, I do. I think it was negative because it was down to
Okay.
begin with. So it came over as a negative and turned positive when it came over. And the reason it was negative is it was down.
Oh, so your first step you did W equals 4 kg times 9.81. So all those values will be negative?
Yeah, all the weights, because they're going down. What you put into an equation is based on what direction you assume it acts. So I assume they were down, so it goes in as a negative. What you get out of the equation tells you whether your assumption was correct or not. So, like I assumed it was negative, I solved for it, the answer comes out positive. The meaning of the positive answer was I was right, it does act down. That's kind of how that goes, Okay. Yeah, question?
Yeah, in physics 211, they kind of encourage leaving the variables until the
Yeah,
absolute
they sure
last
do.
second, and I do get slightly different values, so I'm not sure, just what you'd like to see on a test. And
Yeah, sure. Okay.
Probably just for
So any other questions on this one, this 2D one? Okay. All right, now the 3D stuff is what we'll do on Monday. Now, and I think I've got this. Yeah, it's in there, isn't it? So 248. So this is page 248. And this, now 3D is a more formal approach, okay? 2D, I look at it, I use trig, I've got some angles, I do the right angle trig, and I figure out the directions on my own. 3D, I take a much more formal approach because there's more going on and it's more complex to visualize it. So in 3D, you got 3 equations and 3 unknowns, potentially. Some of fx, some of fy, and some of fz equal to 0. So what I'm going to do this in a very regimented sort of way. I'm going to write out all the forces as x, y, z Cartesian vectors. Even the unknown forces. I'll find the unit direction vector for unknown forces, and then run the force magnitudes as unknowns through the unit vectors. Then I'll build a matrix. the rows are X, Y, and Z directions, the forces are put in columns, and then I go ahead and solve out the matrix. And that's all right on page 248, that list of instructions, but that's how I approach a 3D problem in a series of steps like that, okay? And of course, we're about out of time, but we'll go through that on Monday. Why don't I get you a couple of these to do, these 2D ones. About 171 and 173. Now, the thing on, let's just look at 173 for a minute, because there's one thing on that I want to emphasize. So 171 and 173, those are due Wednesday, which is the 11th, I think. All right. Now, let's just look at 173, because there's one thing about that sketch that can be a little confusing, and I want to clarify it while I'm thinking about it. So, homework, here we go. Now, what I'd like you to do with 173 is find the angle of this cable. And on 173, and this is shown on page 5, I think. Yeah, page 5 is where it is in your packet there. And also 5A. A and F are not at the same elevation. You can't assume that, all right? Okay, so you find the angle of DF. And that's what I'm asking you to do, is to find the angle of DF by using equilibrium. That's how you'll do it. Not geometry, but by using equilibriums. Okay? Equilibrium. There we go. Okay? So just a little bit of, that tends to be confusing. People see A and F, they tend to think they're at the same elevation, but they're not. It's not the assumption there at all, okay? So just use equilibrium to find the angle of DF.
Which problems are due?
171 and 173. Okay. So 171 and 173.